Start.
Good afternoon, everyone. The main goal for today would be to determine whether a binomial of the form x minus c is a factor of a polynomial, and for today we are going to confine ourselves to the binomial of this form. And when I say this form, I mean the form, linear form, where the highest power of x is 1 and the coefficient of x is also, in this case, as you can see, is 1. Can we do it for the coefficient different than 1? Yes, certainly we can do that. But for today we are going to confine ourselves with this form. And this is the form that we have been working on with previously with the long division and synthetic division. So in order to answer this, we are going to use a combination of these three things. We are going to use the synthetic division, which is a very useful method, and we talked about this method yesterday. And then we are going to use the combination of remainder theorem and the factor theorem. Again, these are theorems that you have informally seen in maybe elementary schools or in middle school, but here we would be a little bit more careful in writing these theorems, and at the same time we'll look at the proof of these theorems, so that we convince ourselves that yes, these theorems are true, and they are true for all different numbers. Okay, so before we try to work with the polynomials, I would like to start with the numbers, and then we'll extend the idea that we use in numbers when we divide a number by another number, and we'll extend that idea to our polynomials. To begin with, I would like to start by asking you these simple questions. The first one would be, what is the remainder? What is the remainder when we divide? So let us look at a few examples. Let us start with simple numbers, and then we are going to extend this to polynomials. We know things, information about numbers, how numbers behave, how we divide, and then we'll extend that to polynomials. So first of all, let us try to see how we divide 15 by 4. Let's also look at an example, 25 by 5. Let's use these two for now. So in order to find the remainder, what was the method? The method was simply, we can use the long division to do that. Well, of course, we can use the long division. So let us set up the long division. 15 divided by 4, we are setting up the long division. We have 4 times 3 is 12, and then 15 minus 12 is 3. So we know that this 3 that we have here is our remainder, and this 15, this is called the dividend. Okay, we know these things from elementary school, right? So we have the remainder, we have the dividend. What is this called? Okay, this guy over here is called our quotient, right? So I will write quotient, and then of course this is called, we are dividing by it, and it has a nice name, it's called the divisor, right? Divisor. So we can similarly find the remainder for this case, and let us do that. We have 25, want to divide this by 5, what do we have? 5 times 5 is 25, and then 25 minus 25 is 0, so this is our remainder. Well, here we are interested in finding the remainder. We have the remainders for both these cases. Now there is a nice way of writing these dividend, quotient, divisor, and remainder, and there's a relationship that they have with each other, and that also goes back to our school, elementary school times. So let us write that relationship between these 4 numbers. And the relationship, if you remember, is something like this. The dividend equals the divisor times the quotient plus the remainder. So we already know that. And let us, for these two cases, if we had to write everything out, what is the dividend for first case? It's simply 15. and that equals the divisor, which is 4, times the quotient, and the quotient is 3, plus the remainder for the first case is also 3. Okay. Similarly, we can write the same thing for part B. We have dividend 25, which equals divisor 5 times the quotient, which is 5, plus the remainder, which is 0 in this case. So we can extend the same idea, like dividend is related to the divisor, quotient, and the remainder. So the same idea we can extend it to our polynomials. So let us look at 2 examples, and from 2 examples we'll try to rewrite the relationship between the dividend, the divisor, quotient, and the remainder, and let's see from there how we can define our remainder theorem and then find the factor theorem. Okay. So let us take 2 examples. Example 1. We want to find the remainder when we divide this polynomial function f of x is a cubic function, x cubes plus 2x squared minus 5x minus 6, and we want to divide this by x plus 1. And we also want to look at another example where we'll take another polynomial function, g of x equals, we have 2x cubes minus 3x squared plus 4x minus 1, and we want to find the remainder when this is divided by x minus 2. Well, in order to find the remainder for these 2 cases, one of the ways is to go back and use the long division. But in the previous class, we did try to look at the long division, and we found out that long division is kind of lengthy and it's kind of more complicated method. So instead of using long division, we have a nice, quick, and useful method, which is called a synthetic division. And we talked about how the synthetic division works, and it's motivated to provide the long division. So our goal here would be then to use synthetic division in order to find the remainder. Alright. So before using the synthetic division and setting up the synthetic division, the first thing that we have to do is, that we talked about, is to make sure that the binomials that we are dividing by are in the standard form. And when we talk about the standard form, we know that the standard form for a binomial that we are using here is x minus c, right? So for number 2, we have x minus 2, so we already have this in the standard form. Well, for number 1, it does not look like in the standard form, but can we rewrite this in the standard form? Of course, we can rewrite this in the standard form. And the standard form in this case would be x. This plus can be written as minus times negative 1. So we have negative times negative, which is positive, so we still have the same binomial, but now this is in the standard form. In the standard form, we can easily identify our c. So we have c for this, and we have c for this. We are all set to write our synthetic division, set up our synthetic division. So for part 1, how do we set up the synthetic division? We start from negative 1, right? And then we have to write all the coefficients of the polynomial. In this case, we are not missing any terms. Please look carefully. We are not missing any terms. We have the cube, square, 1, and next to the zeros. So we don't have to introduce any zeros or any other numbers. So we can go ahead and write the coefficients. We have 1, 2, negative 5, negative 6. These are the coefficients for our polynomial function. Now, in order to use the synthetic division, the method is we just bring this 1 down, then multiply 1 and this, 1 and negative 1, that gives us negative 1. Then we add these two, so 2 and negative 1 gives us 1. So you have to be careful here. Usually with the long division, we subtract the second number from the first term, right? We subtract the second number from the first term, but the synthetic division, it works different. We add the numbers. Now I see students make mistakes all the time because we're so used to using long division all the time, and that's what we have learned in our elementary schools and middle schools. So we tend to make that mistake, but be careful. In the synthetic division, once you do the second step, we have to add. Okay. So we have 1, then again the same thing, 1 times -1 is -1, -5, -1, when you add them we get -6, the -6 times -1 gives us 6, and finally 6, -6 and 6 add up to give us 0. So we can write our quotient and remainder here. So we have the quotient, and we know that if the highest power of the dividend is cubic, then the highest power of the quotient would be 1 less than that. So in this case, it's going to be a quadratic, where the highest power of x is 2. So, and these 3 are the coefficients for that quadratic polynomial. So we have x squared, we don't have to write 1, it's understood, plus again 1 times x, we don't have to write 1, it's already understood, and then -6, which is the constant. And also the remainder, which is always the last number of the final row, and in this case it's 0. Similarly, we have the remainder and quotient. Similarly, if we set up the synthetic division for the part 2, we can also find the quotient as well as the remainder. So let us quickly set up the synthetic division for 2. We already have C2, and then the coefficients. Again, this is all in the nice form. We are not missing any powers of x. We have cube, square, 1, and x to the 0, right? So we can write the coefficients: 2, -3, 4, and -1. And then following the same method, bringing 2 down, we have 2 times 2 is 4. Adding this, we have 1. 1 times 2 is 2. 4 times 2 is 6. And we have 6 times 2 is 12. And then 12. And when we add -1, what do we get? We get an 11. So if we have to write the quotient and the remainder in this case, the quotient would be 2x squared plus x plus 6, and the remainder will be 11. So we already learned about the synthetic division, and we can use synthetic division to find the remainder, and in addition to the remainder we can also get the quotient in both the cases. Now we are just going to extend the idea that we already know from the numbers to our polynomials, which is this piece here, where we have a relationship between the dividend, divisor, quotient, and the remainder. So when I say that, I mean to say that we want to write for part 1, the dividend is f of x, right? The dividend will be equal to the divisor. What is the divisor in this case? It's x plus 1. We are talking about the polynomials. So we have x plus 1 times the quotient. And the quotient that we have obtained by using the synthetic division is this piece here. X squared plus x minus 6 plus, we have to add the remainder, and the remainder here is 0. Okay, so we simply extended the idea that we already knew for the numbers to our polynomials. And we can do the same thing for number 2. We have g of x, which is our dividend, that equals the divisor x minus 2 times the quotient, which is 2x squared plus x plus 6, the quotient that we obtained by synthetic division, plus 11, which is our remainder. Okay? So far so good. So far we have been able to use the synthetic division to find the quotient and the remainder. We found the quotient and the remainder, and then we went back to our basic elementary math, and we wrote the relationship between the dividend and the divisor, the quotient and the remainder, right? So now we will look at some important things carefully. Let us try to evaluate these functions. Let us try to evaluate these polynomial functions, these two polynomial functions, and I will choose particular points. For the first one, I will choose -1. And for the second one, I will choose 2. Let us try to evaluate these two polynomial functions at these points, -1 and 2. In a second, you will see why we want to use these points to evaluate these functions. So how would you evaluate? Let us say this function, this polynomial function here at x equals -1. Well, there are two ways. One of the ways would be, you take this -1 and substitute here, because this is our original f of x, right? So we substitute x by -1 and simplify, and we get the value of this function at x equals -1. Same thing for part 2. We can substitute, go back to g of x, substitute x by 2. Substitute x by 2 for all the x's. Right? Substitute x for 2 for all the x's and find the value for the function at 2. That would be certainly one of the ways. Well, we also can use a more convenient and easy way. And the easy way could be if we rely on this and this rather than going back to these two. Look carefully. If we use this, see, it gets so simplified. If we use this, you have to substitute x by -1. If we substitute x by -1 in this, what do we get? -1 plus 1. -1 plus 1 is 0. We don't really care what happens here because we already have a 0, right? And 0 times any quantity is also a 0. So we have a 0 times 0, which is 0, and then 0 plus 0, which is still a 0. So what do we get? F at -1 is simply 0. And we could have obtained the same thing, exactly same thing, if we substitute this -1 for x, and x here, and simplify. But that would take a little bit more time. This was much easier, quicker. Okay. Same thing we can do for the second part. X equals 2. If you substitute x equals 2 in here, what do we get? 2 minus 2 is 0. Again, 0 times, we don't really care what happens here. So 0 times any quantity is still 0, right? And 0 plus 11 is simply 11. So if you look carefully at these two numbers and these two numbers, you can see that we have, these two numbers are the same numbers that we have in here, the C's. The C for the first case and the C for the second case, right? And these two numbers on the right, let us look at this one first. What is 0 here? For the first case, 0 was our remainder, right? And we have a 0 remainder here. For the second case, what was the remainder? The remainder was 11. We have the same number 11 here. So it turns out that we can find the remainder. We can find the remainder, well, we can certainly find it by using the synthetic division, but we can also find the remainder by using these points, -1 and 2. By using these points, -1 and 2 in the original function, that would also give us the remainder. Okay? And this is what the remainder theorem says. So what we said was an informal way of saying the remainder theorem. Now let us formally write it and it will be more clear to you. So let us formally write that. So for these two cases, we could simply say that the function values